One formula computes a vector perpendicular to two others, the area they span, the volume of a slanted box, and even proves the law of sines. That formula is the cross product in components. We build it from 3 unit vector products, then put it to work on 5 problems. Start with the unit vectors I hat and the j hat. The magnitude of I hat cross j hat equals 1 times 1 times the sine of pi over 2, which is 1. By the right-hand rule, curl your fingers from I hat toward j hat, and your thumb points along positive k hat. So I hat cross j hat equals k hat. The pattern cycles around. J hat cross k hat equals I hat, and k hat cross I hat equals j hat. Reverse any order and the sign flips. For example, j hat cross I hat equals negative k hat because the cross product is anti-commutative, and any unit vector crossed with itself is 0 since the sign of 0 is 0. These 9 products unlock the component formula. Let's take a special case first. Suppose vector b points along the positive x-axis, so b equals b sub x times I hat. Meanwhile, vector a keeps all 3 of its components. Now distribute the cross product term by term. The first term, a sub x times b sub x times I hat cross I hat, vanishes because a vector crossed with itself is 0. The second term, a sub y times b sub x times j hat cross I hat, gives negative a sub y times b sub x times k hat. The third term, a sub z times b sub x times k hat cross I hat, gives a sub z times b sub x times j hat. So this special case collapses to negative a sub y b sub x in the k hat direction, plus a sub z b sub x in the j hat direction. Now generalize to an arbitrary b with all 3 components. The same expansion yields the full formula. Across b equals a sub y b sub z minus a sub z b sub y in the I hat direction, plus a sub z b sub x minus a sub x b sub z in the j hat direction, plus a sub x b sub y minus a sub y b sub x in the k hat direction. Notice the cyclic pattern. Each component skips its own axis, cycling through x, y, and z. The same structure holds in cylindrical coordinates. Here are hat points radially outward in the plane, theta hat points tangentially, and the k hat points perpendicular to the plane. These 3 are mutually at right angles and form a right-handed set, so their cross products follow the same cycle. R hat cross theta hat equals k hat, theta hat cross k hat equals r hat, and k hat cross r hat equals theta hat. Reverse any pair and the sign flips. Each unit vector crossed with itself gives 0. The right-handed structure, not the specific coordinate system, drives these rules. Let's compute 1. Vector a equals 2i hat minus 3j hat plus 7k hat. Vector b equals 5i hat plus j hat plus 2k hat. For the I hat component, we take a sub y times b sub c minus a sub c times b sub y, which is negative 3 times 2 minus 7 times 1. That gives negative 6 minus 7, which equals negative 13. For the j hat component, we take a sub c times b sub x minus a sub x times b sub c, which is 7 times 5 minus 2 times 2. That gives 35 minus 4, which equals 31. For the k hat component, we take a sub x times b sub y minus a sub y times b sub x, which is 2 times 1 minus negative 3 times 5. That gives 2 plus 15, which equals 17. So a cross b equals negative 13 I hat plus 31 j hat plus 17 k hat. The cross product proves geometry too. Take a triangle with interior angles alpha, beta, and gamma with its sides represented by vectors a, b, and c arranged head to tail, so that a plus b plus c equals 0. Now cross vector a into the entire sum. The self term across a vanishes, since any vector crossed with itself is 0. That leaves a cross b plus a cross c equals 0. So a cross b equals the negative of a cross c, which means their magnitudes are equal. From the triangle's geometry, the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of gamma. And the magnitude of A cross C is the magnitude of A times the magnitude of C times the sine of beta. Set these two equal, cancel the common magnitude of A and rearrange. The magnitude of B over the sine of beta equals the magnitude of C over the sine of gamma. Repeating the same trick with vector B crossed into the sum gives the magnitude of A over the sine of alpha equal to that same ratio, and that is the law of sines. Need a direction perpendicular to a plane, cross two vectors lying in that plane, and then normalize. Vector A equals I hat plus j hat minus k hat. Vector B equals negative 2 I hat minus j hat plus 3k hat. Now apply the component formula for the cross product. The I hat component is 1 times 3 minus negative 1 times negative 1. That's 3 minus 1, which equals 2. The j hat component is negative 1 times negative 2 minus 1 times 3. That's 2 minus 3, which equals negative 1. Be careful with the sign here because the x component of b is negative 2, not positive 2. The k hat component is 1 times negative 1 minus 1 times negative 2. That's negative 1 plus 2, which equals 1. So A cross B equals 2 I hat minus 1 j hat plus 1 k hat. Its magnitude is the square root of 4 plus 1 plus 1, which is the square root of 6. Dividing the vector by its magnitude gives the unit normal with a plus or minus sign, since the two opposite directions are both perpendicular to the plane. Now let's talk about volumes. A parallelepiped is a slanted box with edge vectors A, B, and C all meeting at one corner. Its volume equals base area times height. Let vectors B and C form the base. The magnitude of B cross C gives the base area, and the direction of B cross C points along n hat, the unit normal to the base. So B cross C equals its magnitude times n hat. The height is the projection of A onto n hat, which is simply the dot product A dot n hat. Now dot the vector A into B cross C. You get the magnitude of B cross C times A dot n hat, which is area times height, exactly the volume. This combination, A dot the quantity B cross C, is called the scalar triple product. The cross product builds the base, and the dot product extracts the height. Finally, dot and cross products together split any vector. Here is the claim. Vector A equals the quantity A dot n hat times n hat plus the quantity n hat cross A crossed again with n hat. To prove it, write A as a parallel times n hat plus A perpendicular times e hat, where e hat is the unit vector along the projection of A onto the plane perpendicular to n hat. Since e hat dot n hat is 0, the dot product A dot n hat picks out only A parallel. So the first piece, A dot n hat times n hat, equals a parallel times n hat. That is the parallel component. Now cross n hat into A. The n hat cross n hat term vanishes, because any vector crossed with itself is 0, leaving A perpendicular times the quantity n hat cross e hat. Cross once more with n hat. By the right-hand rule, the quantity n hat cross e hat crossed with n hat is a unit vector pointing right back along e hat. So the second piece equals a perpendicular times e hat, the perpendicular component. Adding both pieces, a parallel times n hat plus A perpendicular times e hat reconstructs the original vector exactly. 3 unit vector products, I hat cross j hat equals k hat and its cycle, generate the entire component formula. The same right-handed structure carries to cylindrical coordinates. With components in hand, the cross product delivers perpendicular directions, triangle relations like the law of sines, base areas and volumes through the triple product, and complete vector decompositions. Master the cyclic pattern once, and every application follows from the same machinery. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.